Hello everyone, welcome back to electrochemistry class. Today I have brought a more interesting and scientific topics, that is the Nernst equation, which is used in electrochemistry. So that is actually to find out the cell potential of a electrochemical cell, right? So what is first question is, what is Nernst equation in electrochemistry? As you know that in the electrochemistry, so there is a redox reactions which are actually supposed to enhance the chemistry. So what is electrochemistry? First thing is that electrochemistry is nothing but it deals with the relation between the electrical energy and chemical energy, right? So once the redox reaction is feasible, then there is a setup of electrochemical cells. And in the previous lectures, what we have studies about electrochemical cell, so it is of two types. So that is electrochemical cell means it is a galvanic cell, and second one is electrolytic cell. So overall, electrochemical cell, right? So it is related to the conversion of chemical energy into electrical energy, right? Or in a reverse order, you can say the conversion of uh, electrical energy into chemical energy. So that actually is explained in the electrochemistry, right? And it comes under the electrochemical cell. So what is electrochemical cell? Electrochemical cell is actually composed of three principal components, that is anode, cathode and electrolyte, right? And as you know that anode is responsible for oxidation and cathode is responsible for reduction, and electrolyte is actually act as a transport medium for for ion exchange reactions, right? So first thing is that my question here is the what is the Nernst equation? Actually, Nernst equation was derived in 1819 Walter Nernst by Walter Nernst, right? So it is a scientist that actually studies about the electrochemistry. So what happens here? Nernst equation gives us idea about the cell potential, or simply you can say electromotive force of the electrochemical cell, right? So at standard state or at non-standard state. So that can be determined through the use of the Nernst expressions, right? So how we will derive Nernst equations? So first we understand what is electrode potential, right? So this is electrode potential, which is actually abbreviated as E. So electrode potential means, as in the previous lectures you have studies about the electrochemical cell. So and each electrode gets a particular kind of potential. So electrode potential means when a metal rod, right? When a metal rod is dipped, suppose it is a metal rod, right? And it is dipped in a solution of its salt, right? So this is salt solution, and when this metal rod is connected with potentiometer, potentiometer, right? So what happens when a metal rod is dipped into the solution of its salt, right, then there is a interface that is generated between metal rod and electrolyte. So this is your electrolyte, right, which contains cation and anion. Now this metal rod, once it is inserted in this electrolyte, then there is a two possibility. So either this metal can get oxidized or it can reduced, right. So depending on the interfacial reactions between these metal rod and electrolytic ions, right. Suppose if this metal is oxidized as M n plus by releasing an electron, right. So there is a potential, right, between metal rod. So metal rod means it is a solid, metal solid, and Mn plus, which is actually in the solutions. So if this is getting oxidized, it means the electron released through the oxidation of this metal rod, then this electron will be accumulated on the surface, right. So it means surface is getting negatively charged, right. And once this metal is oxidized, it means metal atom undergo into the solution as a M n plus. So solution gets positively charged, right. So there is a potential actually positive charge around this rod, right, and negative on the surface of this rod. So this metal is negatively charged because of presence of released electron on the surface, and solution becomes positively charged. So there is a negative charge and positive charge in this medium. So there is a generation of potential, and the potential which is generated on the surface of this electrode is called electrode potential, right. So this is electrode potential, and this potential is measured through potentiometer. So once potentiometer is connected through this metal rod, so then we can simply read the value on potentiometer, and we can assign it as a electrode potential, right. So this is electrode potential. Since metal rod gets oxidized in the solution, right, so the potential which will be generated on the metal rod will be oxidation potential, right. So the electrode potential is called oxidation potential. So this is oxidation potential, and it is designated as E ox, right. So oxidation potential. Suppose if there is a possibility of reverse reaction, it means if there is a chance of M n plus n electron, it is getting back M solid, right. So here this is the reduction reactions. It means the cation from the electrolyte solutions getting electron from the surface of metal rod, and it is reduced back into the metal salt, right. So this metal cation in the solution receives electron from the surface, and it will reduced, and it will deposit it on the this rod, right. So this is the reduction reaction. So the potential which is generated at this metal electrolyte interface will be reduction potential, right. So this is reduction potential, right? So in case of reduction potential, what happens? So there is metal will be positively charged, and around this metal there will be negative charge, right? Because of presence of uh, anions in the electrolyte solutions, and some cations actually flows towards this rod, and actually it is reduced. So metal rod receives cation, so it is getting positively charged, and the concentration of cation is decreases in the solution, and concentration of anion is increases in the solution, so solution is negatively charged and metal rod is positively charged. So there is a interface between this positively charged metal rod and this negatively charged electrolyte solution, and hence the potential that will be generated, right, can be read by potentiometer, right? PM, that is called potentiometer. So it is called reduction potential, right? So this is your E read, right? So this is your reduction potential. So we have a two kind of potentials, that is oxidation potential, and that is second one is reduction potential. So this is the generation of potential when a metal rod is dipped into the electrolyte solutions. Okay. Now the next point is, what is standard electrode potential? Standard electrode potential means uh, standard electrode potential, electrode potential, the definition is same. Only thing is that the condition at which we are going to measure the potential of the electrodes, right? So suppose we are measuring electrode potential at standard state. Standard state means temperature of the electrolyte solution must be 298 Kelvin. It means 25 degrees centigrade, right? And the concentration of the electrolyte solution must be, electrolyte contains positively charged and negatively charged ions, so both have concentration that equal to 1.0 molar, right? And the pressure of the measurement, that is pressure 1 atm, 1 atmospheric pressure. So temperature, pressure and concentration, if it is fixed at standard state, then the potential generated at the interface of electrode and electrolyte is called standard electrode potential, right? So this is designated as E naught, right? So if there is a oxidation which occurs generally at the anode, so that is E naught ox, right? So if there is a reduction between electrode and electrolyte, then it is E naught read. So it is a standard oxidation potential, right? So this is a standard reduction potential. So there is a two possibility. So because of the redox reactions which are occurring at the interface between electrolyte and electrode. So this is the difference between electrode potential and standard electrode potential. So standard electrode potential means at standard state. So now in the previous lectures, what you have studied? this is zinc, copper, Daniell cell or galvanic cell. So you have studies, right? Galvanic cell. Here two type of metal rods are connected through salt bridge. In the previous lectures, what I have justified here, zinc metal rod, actually they are dipped in zinc sulfate solution, and copper metal rod, they are dipped in copper sulfate solution, right? And both these rods and both these solutions, they are connected with salt bridge, right? So they are connected with salt bridge. And the salt bridge actually complete the redox process through maintaining the ion balance, right? So the cell actually is composed of anode and cathode. So here one metal acts as a anode while other metal act as a cathode. So in this galvanic cell, zinc act as a anode, right? So and copper act as a cathode. So because of the electrode potential, as in the previous lectures I have actually shown you that when zinc gets oxidized, Zn2 plus 2 electron, right? So it has standard reduction potential, that is minus 0.76 volt, right? So this is standard reduction potential, standard reduction potential. And when copper, right, is reduced at cathode by receiving the electrons, it is copper solid. Now the standard electrode potential for this kind of half cell reaction, that is E naught is equal to 0.34 volt. So this reaction occurs at cathode. So cathode potential is higher because of positive 0.34 volt, and this occurs at anode, right? So anode potential is lower because it has negative value. So both these values are standard reduction potential, and standard oxidation potential is negative of standard reduction potential, right? So what will be the opposite value? That will be negative of the standard reduction potential. So if it has half cell reaction like that, then if you want to get E naught Zn 2 plus, then it will be 0.76 volt, right? So because Zn is getting oxidized from Zn to Zn2 plus, so oxidation potential, that is standard oxidation potential, will be 0.76 volt, right? Now for this particular half cell reactions, so here E naught Cu2 plus is reduced to Cu, so Cu2 plus Cu, that will be here it is actually standard reduction potential 0.34. So if you want to reverse these reactions, it means E naught Cu2 plus, then it has value negative of that 0.34, so minus 0.34 volt, right? So this is the actually standard reduction and oxidation potential, and standard oxidation potential will be the negative value of the standard reduction potential, right? So it is clear. Now we are reaching towards Nernst equation. What is Nernst equation, right? This is your Nernst equation. So this is the most important mathematical equations used to determine the cell potential under non-standard conditions. Okay. So in 1890, Walter Nernst has derived an expressions uh, through the application of redox reactions and by using electrical energy. So the Nernst equations, how it is derived, suppose we have a metal, right? So this is metal, and if it is dipped into its salt solution, then there will be potential. So there is a two possibility: this metal can be oxidized or this metal can be reduced, right? So suppose this metal is reduced, so it means Mn plus n electron, so it is getting back to M solid, right? Now in the chemistry, in the thermodynamics, you have studies about reaction quotient, that is Q. So Q is reaction quotient, and this Q is actually concentration of M in solid state, concentration of Mn plus, right? So this is reaction quotient, and you know that change in Gibbs free energy is related to standard Gibbs free energy in such a way ln Q, right? So delta G is equal to delta G naught plus RT ln Q, where delta G is change in Gibbs free energy, right? At any temperature, suppose at T temperature, and this is change in Gibbs free energy at standard state. It means we have defined earlier what is standard state, and R is the gas constant, so it has value 8.314 joule per Kelvin per mole, right? And T is the temperature in Kelvin, and ln is the natural logarithm base E, and Q is called reaction quotient, right? So this is reaction quotient, Quotient. So this is reaction quotient. Here metal is actually inserted in the electrolyte solutions containing cation and anion, and if electrolyte cation getting reduced on the surface of metal rod, then there will be reduction potential, right? So reduction potential means E.M.N plus to M. So this is reduction potential at any temperature, and standard state, so this is E naught M n plus then M. So this is standard reduction potential, and this is standard this is reduction potential at any temperature, and this is at 298 Kelvin temperature. Clear? Now this delta G is actually related to the temperature and reaction quotient, right? So as you know that in the electrochemistry, delta G is equal to N F E cell, right? So cell is actually when both anode and cathodes are present in a electrolyte medium, then there will be setup or construction of the cell. But suppose if there is a single electrode reactions, so single half cell reactions, single half cell reactions. So there will be electrode potential. So this change in Gibbs free energy will be equal to minus NFE cell. So what happens here? Delta Z, by putting these values in this equation. This is equation 1, this is equation 2. The value of delta Z is actually kept in this equation first. So minus N F E, right? So is equal to, at standard state, then minus N F E naught plus R T ln Q, right? So what happens here? E is equal to, we just cancel the minus from taking out it. So that will be E naught minus RT upon NF ln Q, right? So this is Nernst equation. Nernst equation means here electrode potential. So there is a reduction. So what happens here? You can showing here, that is M n plus n electron. This is getting back M solid, right? So E M n plus then M, right? So E naught M n plus then M minus R T ln Q, right? So this is the complete expression of the reduction reaction, and at any temperature T and at temperature 298 Kelvin, right? So here electrode potential depends on the temperature and reaction quotient, these two parameters. If you change the temperature and reaction quotient, then the value will be reduced, because E naught M n plus M is a fixed or constant value. So the value of this E depends on temperature and reaction quotient. So if this value increases, means this value decreases, right? If it is decreases, and then if there is a low value, then there will be high value, right? So if there is a high value, then there will be low value. So depends on the difference between these two values, right? So these values and these values का difference, that will gives us idea about the electrode potential, right? So Q is equal to, what is Q? Q is equal to, that is M, concentration of M, right? So this is actually what is here happening. So this is your concentration of M upon concentration of Mn plus, right? So the concentration of M in the solid state or free state, concentration of metal is treated as 1 molar, right? So it will be actually 1 by Mn plus. So what happens in this reactions? So E M n plus M is equal to E naught M n plus M minus R T ln. So 1 by m n plus, right? Here we have missed NF, right? So this is NF. So depends on these value, this electrode potential changes, right? So here the concentration of electrolyte cation is exist in denominator, right? So depending on the concentration of this particular electrolyte cation, the value of this part will. So if this value is very high, then the potential will be low, right? So this is actually electrode potential if single electrode reaction is reduction reactions, right? Similarly, if there is a possibility that metal can be oxidized, so suppose if there is M solid, it is getting M and plus N electron. So if there is a oxidation between the electrode and electrolyte, so then oxidation potential, so by putting the value, it will be E.M. M n plus, right? So equal to E naught M n M, and this is actually getting M n plus. So it is actually oxidation. So zero oxidation state, or here n plus oxidation state, minus RT upon NF, and here ln concentration of M n plus, right? And concentration of M. So here concentration of M 1, right? 1.0 molar in the free state, right? So what happens here? E M M n plus is equal to E naught M M n plus minus RT upon NF ln M n plus. Now the resultant electrode potential changes with this right? So in this value, so if this value is low, then there will be high electrode potential. If this value tending towards higher value, then the potential will be low. So this changes according to the value which is solved for this part, right? So this is these are the two actually Nernst equations for cathodic reduction reactions and for anodic oxidation reactions, right? So what happens here, as you know that in case of if these two actually reactions are coupled or added to each other, then there will be a complete cell reactions, and hence you will getting cell potential or electromotive force. So that is equal to E cell is equal to E, that is cathode C minus E anode, right? So this is the cell potential, which is the difference between reduction potential of the cathode and reduction potential of the anode. So that will be a cell potential. But this cell potential only it is when obtained if there is a presence of two half cell reactions and completing the electrochemical cell, right? So here this is single electrode reactions, and in the previous page also this is also for single electrode reactions, right? Single electrode reaction. So single electrode reactions means there is only reduction. So reduction potential, we are getting reduction potential, right? So this is actually difference between the standard reduction potential minus this value, right? Now this is also for single, this is your single electrode reactions, electrode reaction. So this is your expression which signifies the value of potential, right? So because it is a oxidation reaction, so here will be oxidation potential, right? So this is oxidation potential of the electrode at a temperature T, and this is the standard oxidation potential at 298 Kelvin, right? And R is the gas constant, T is the temperature, and is the number of electron transferred in this particular reaction, and F is the Faraday constant, which has value, you know, that 96,500 coulomb per mole, right? So this is the expression for the measurement of electrode potential if there is a single electrode reaction occurs in electrolytes, right? But when two half cells are connected to each other to form an electrochemical cell, then there will be a electromotive force or cell potential because of the formation of the electrochemical cell. Either electrochemical cell means or galvanic cell or electrolytic cell, right? So what happens? Suppose we have zinc copper, right? So we have zinc copper galvanic cell, galvanic cell. So in the previous lecture, what you have seen, zinc solid plus copper sulfate aqueous, right? So the reaction is proceeding like that: Zn SO4 aqueous and plus copper solid. Here what happens here? Zinc rod, right? And this is the electrolyte solution where Cu2 plus exists as a electrolyte cation. So from the electrolyte solution, copper is precipitated as copper solid, right? So zinc rod has, suppose if zinc rod is dipped in copper sulfate solution, right? So this is your copper sulfate solution aqueous, and if there is zinc rod, right? So this is zinc rod, so it has capacity to react with copper sulfate. So once this zinc rod is dipped in the copper sulfate solution, then copper is displaced from the electrolyte solution and zinc is inserted in the electrolyte solution. So it forms zinc sulfate and it is precipitated out copper solid. So this is the spontaneous reactions, because in the zinc copper galvanic cell, in the previous lectures we have seen that E naught cell is equal to 1.10 volt, right? So because E cell is positive value, so delta G will be minus NF E naught, so E naught cell, so it will be negative value. So reaction is spontaneous, right? Spontaneous. So this is the beauty. One metal can displace another metal from the solution if the reaction is spontaneous. So there is a prediction of reactions, whether it is occurring in the electrolyte solution or not. So that can be predicted through the measurement of cell potential and change in Gibbs free energy, right? Now, if you want to derive the expression for this particular electrochemical cell, then what happens? So suppose this is your zinc solid, it is oxidized. It means that is your, this is your Zn2 plus 2 electron, right? So this is first equation, right? So here this is your oxidation reactions. So this is your oxidation reaction, oxidation half cell. So the electrode potential will be oxidation potential. So what is the value of E Zn to Zn2 positive, right? Because Zn 0 to 2 plus, it is getting oxidized. So oxidation potential is equal to E naught Zn to Zn2 plus minus RT upon NF and ln Q, right? So Q will be here, this Q will be directly, we can put the value of Q, the concentration of Zn2 plus and concentration of Zn, right? So here again this value will be 1.0 molar, right? Now similarly, if copper 2 plus 2 electron, so that receives from the cathode, then it is converted back to copper solid. Now this is a reduction reactions, right? So this is your reduction reaction. So there will be reduction potential. So what will be the electrode potential for this copper 2 plus and copper? That is ECU2 plus then copper is equal to E naught Cu2 plus copper minus RT upon NF ln, then again reaction quotient will be concentration of copper upon concentration of copper 2 plus, right? Here N will be 2 for both reactions, right? Because 2 electrons are involved between these two entities, right? So this is the actually oxidation potential and this is the reduction potential. And as you know that the cell potential will be E cell E copper 2 plus to copper minus E, that is equal to Zn 2 plus to Zn, right? So both are the standard, both are the reduction potential. So here it is converted through oxidation potential, right? So this will be the cell potential. Now what happens in the previous page, this is your for the so this is your the value. Now right, this is the value. Or simply you can solve this by just adding. So what happens is cell is equal to these two values should be reduced. First these values should be taken. So what will be the value? So E cell is equal to and E naught Cu2 plus 2Cu minus RT upon 2F ln Cu2 plus, right? Minus E naught Zn2 plus minus RT upon 2F ln 1 by Zn2 plus, right? So this is your value. Now this is your 1 by niche. So now it can be written as 1 by Cu2 plus, right? Now what happens? E0 Cu2 plus Cu minus RT upon 2F, we can take it out, and this will be ln 1 by Cu2 plus, right? And this minus minus plus, and this will be equal to, this is minus, and this will be equal to minus minus plus minus plus, and minus out, then this will be minus ln 1 by Zn2 plus, right? So this will be, and that will be minus E. So here one parameter is lefting, that will be minus E naught Zn2 plus, right? So this value will be E0 cell, right? Minus RT upon 2F. So what happens here? If it is going upside, then it will be minus ln, and this is Cu2 plus, right? Minus ln, it is getting 1 by Zn2 plus, right? So then it will be E cell minus RT upon 2F, right? So here no use of this, so only you can put this value in upside, so then it will be positive. So ln Zn2 plus upon copper 2 plus, right? So the cell potential E cell E naught cell minus RT upon 2F ln Zn 2 plus upon copper 2 plus, right? So this is the Nernst equation for zinc copper galvanic cell. Okay, students. So this is the Nernst equation for zinc copper galvanic cell. Now the cell potential or E.M.F of the cell that will be actually this is at any temperature, this is at standard state, and RT upon 2F, 2 is the number of electron transferred in the redox process, and ln Zn2 plus U2 plus. So here the concentration of zinc 2 plus and concentration of copper 2 plus decides the overall these values, right? So if this value is low, then E cell will be high, right? So E cell will be high and R E cell will be low. So after time, what happens in these reactions? Zn plus Cu2 plus and now Zn2 plus plus copper, right? So this is the overall reactions. So after passage of time, what happens? The Zn changes into Zn2 plus. It means the concentration of zinc 2 plus increases, right? So concentration of zinc 2 plus increases, and initially concentration of copper 2 plus is very high, but after some time this copper 2 plus is reduced as a copper solid. So concentration of Cu2 plus decreases, right? So overall the concentration of Zn2 plus increases, means this overall this part will be low, not low, because Zn2 plus is numerator, so the value will be high. So it will be subtracted from E naught, so the E cell decreases, right? So after passage of time, so what happens here? The concentration of zinc 2 plus increases and concentration of copper 2 plus decreases because of the precipitation of the copper as a copper solid. So by putting the concentration of these two ions in this particular Nernst equation, we can solve the resultant cell potential arising from the combination of these two metals, zinc and copper. Now what happens? Actually we can convert this ln into log, right? So this is your E cell will be E cell minus 0.0591 upon n log Zn 2 plus upon copper 2 plus. So log here 10 base, here E base. So in both way it can be measured, right? So after some times there may be chance that E cell always decreases, means once electrochemical cell formed, there is a decrease of cell potential after time, because the concentration of zinc 2 plus is very very high and concentration of copper 2 plus is very low, it is negligible. So it approaches almost E naught cell, and the value of this part will be approx equivalent to E naught cell. So E naught cell and this value will be equal to 0. So after a time E cell will be 0, right? So if there is a zero potential in the electrochemical cell, then it is supposed to be the cell reactions are in equilibrium, right? So now this is equilibrium, and if this reactions occurs as in equilibrium, then reaction quotient can be converted into K. So now this is K, K equilibrium constant, right? So this is equilibrium constant. It depends on the temperature. Equilibrium constant, right? So what happens here? E cell, E naught cell minus RT upon N F ln K. So if E cell is 0, right? So E cell equal to RT upon NF ln K, or ln K NF E0 or E naught cell upon RT. Here ln K, right? So natural logarithm of equilibrium constant depends on the cell potential at standard state and temperature, because n is the number of electrons which is constant, f is the Faraday constant which is constant, and temperature is variable, and E naught cell is variable, right? So the equilibrium constant, if K is greater than 1, right? So E naught cell will be greater than 0, okay? So equilibrium constant must be greater than 1 if you want to get E naught cell greater than 0. So first condition. And second condition is that if you want to K is less than 1, then E naught cell will be less than 0, right? So this is the second condition. So in this case, delta G will be positive, and in this case, delta G will be negative. So this favors spontaneous reaction, and this favors non-spontaneous reactions, and it favors formation of product, right? Formation of product, and this favors formation of reactants, right? So this is the way by which we can show the value of equilibrium constant, right? Now what happens in the previous examples, we have shown that a lot of actually reactions. So this is the value. So this is the actually expression for the rate constant now for these reactions, okay? Now where is the examples that I have shown? So this is the, yes, this is your yes. Now you can see this is the example of zinc copper galvanic cell or Daniell cell. The complete cell reaction is like that, and the standard cell potential. So this is the standard cell potential. E naught cell is equal to 1.10 volt. It means the reaction is spontaneous because E naught cell is positive quantity, right? So it is actually clear. Now suppose after 1 minute we want to calculate the cell potential. Initial standard cell potential is 1.10 volt. It means if the concentration of copper 2 plus and zinc 2 plus is 1 molar at 298 Kelvin, right? Now after 1 minute, the concentration of copper 2 plus is 0.05 molar and the concentration of zinc 2 plus is 5.0 mole, right? So it means concentration of zinc 2 plus increases and concentration of copper 2 plus decreases, right? It's clear from the concentration. Okay. Now by using the Nernst equation, E cell is equal to E naught cell 0.059 1 or 2, sometime somewhere 1 is written because it is the value. So 0.591 volt upon N, and this is log Q. So by putting these values, standard cell potential 1.10 volt minus 0.0591 upon N. N for these reactions, actually Zn going Zn 2 plus 2 electron. So N is equal to 2, right? So here 2 is kept because the number of electron transferred in this cell reaction is 2. And log, so this is Q, and the value of zinc 2 plus is 5 molar and the value of copper 2 plus is 0.05. So after 1 minute, the concentration of zinc 2 plus is high, it is 5 molar, but the concentration of copper 2 plus is very, very low, so it is 0.05 molar, right? So after putting these values in this particular Nernst equation, what we will get? So we get the E cell is equal to 1.04 volt, right? So the cell potential is a positive quantity here also, that is 1.04 volt. But initially it was 1.10 volt. So potential is decreasing, right? It means our electrochemical cell is going to be discharged. So after discharging the electrochemical cell, the cell potential is decreased, right? And a time reached where the cell potential gets the value 0 volt. It means the battery is going to be dead or electrochemical cell is going to be dead, means E cell is 0, right? So if we have a electrochemical cell or any battery that is fully charged, right? But after some times what we have observed that the cell potential is decreases. From this example you can clearly see here it was 1.10 volt initially, but after passage of time it is getting the value of 1.04 volt. It means the potential is decreases after time, right? So because electrochemical cell is going to be discharged after a time. So this is the way by which we can determine the cell potential after passage of time. So another example that is most important here, zinc silver galvanic cell, right? So this is the complete cell reaction. Zinc 2Ag plus, it is getting Zn2 plus and it is precipitated as 2 mole of silver, and the standard cell potential for this particular reactions is 1.56 volts. So it is positive quantity and it confirms that this reaction is spontaneous and it is moving in the forward directions. So it favors the formation of zinc 2 plus and it is precipitated the silver as a silver, right? So what is the cell potential for this particular reactions? So as you know the Nernst equation, E cell is equal to E naught minus 0.0591 upon n log k, right? So here the value of n will be 2 because Zn getting oxidized into Zn2 plus 2 electron, right? And Ag plus electron, it is getting Az, but by balancing these electrons we just multiply by 2 to both side, right, of this equation. So overall we will get such type of cell reactions. So n is equal to 2, right? Now the value of zinc 2 plus and the concentration of Ag plus is like that. Here the value of zinc 2 plus is 10 to the power minus 3 molar. So in the question it is actually given the value of zinc 2 plus after a time it is 10 to the power minus 3 molar, right? But the value of Ag plus is 10 to the power minus 1. It means these reactions proceeding spontaneously after passage of time, the formation of zinc 2 plus is increases and the formation of Ag plus is actually decreasing. So it is converted back to Ag. So what happens here? The overall value is 1.5895 volt. Here overall value is 1.56 volt, right? Here cell potential is increasing. Here cell potential is increasing. Here cell potential is decreasing. It means what? It means the reaction is actually getting reverse because here concentration of Ag plus is high, right? Concentration of Ag plus is high and concentration of zinc 2 plus is low, right? Low and this is high. It means the reaction is going in the backward directions, right? So the since potential is getting increasing, it means electrochemical cell is going to be state of charging state. So after the charging, the electrochemical cell or battery gets actually its original potential or increased potential. So here the cell potential are actually increased, found to be increased with respect to the standard state cell potential, right? So this confirms that the reaction is occurring in the backward directions because the concentration of the silver plus is increases, right? So this is the way by which we can understand the significance of Nernst equation and the measurement of cell potentials at a particular temperature T or at any standard state to 98 Kelvin, right? So these are the value, and you know that E cell E naught cell minus 0.0591 upon n log k, right? So this is the actually relations, next relation between the cell potential and equilibrium constant. But at equilibrium, E cell attains the value is equal to 0 volt, right? So by putting the value of E cell 0, it will look like that. Log k is equal to n E cell upon 0.59 1 volt. So this is actually the equilibrium constant. Equilibrium constant depends on the standard state cell potential, right? So if this value varies, and accordingly this k will be changed. Now this reaction, what does by this equation, what does you mean by this equation? Actually here standard state cell potential is 1.56 volt for these reactions. It means Zn is oxidized and silver is reduced in this equation, and the k value is very high, right? It is by putting this value here and by putting the value of n for this reaction is 2 and 0.0591, and by taking ND log, after the final calculation we get the equilibrium constant k is equal to 1 multiplied 10 to the power 52. So k is equal to 10 to the power 52. It is a very high value, it means equilibrium constant is very very high, and that favors the formation of the zinc 2 plus, right? It means when zinc rod is uh, inserted in silver nitrate solutions, then it is precipitated out. It means zinc have a tendency to displace the silver cation into as a silver metal, right? So this reaction is spontaneous and it is thermodynamically feasible because the equilibrium constant for this reaction is very very high. It has 10 to the power 5 2. It is a very very high quantity. Okay, so now I think this much is sufficient to understand the significance and relation of the cell potential at temperature T and cell potential at standard state, right? So there are a lot of examples that can be taken from the reference, and you can understand what happens when electrochemical cell is getting charged or getting discharged. So after discharging, cell potential decreases and a time reached at which cell potential becomes 0, and then we require to charge it again if it is rechargeable, right? So now this is the final equations, and right, so I think this much is sufficient to understand the electrochemistry of the redox process and the relation between the cell potential and temperature and equilibrium constant. So thank you students for listening and watching this particular video lecture, and if it is beneficial, comfortable, please don't forget to like, share and comments. Okay, thank you.